Welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. As we have said in our last class, today in this class we will be first talking about how to model YYg transformer, followed by how to model a DD transformer, that is in a transformer in which both the primary as well as the secondary windings are delta connected. So, first let us look at a transformer which is YYg connected. So, first let us look at YYg transformer, say YYg0, say YYg0. Of course, the same procedure will hold good for any YYgx transformer where x is equal to 2, 4, 6, 8, 10, but we will be only looking at the process of so this is A1, A2, B1, B2, C1, C2, A1, A2. So, after that what we do is that we, as usual, we connect A2, B2, C2 together, but because it is not grounded, so we do not ground it, and then this is from phase A, then we say this is phase B. Phase C, and then we do the phasor diagram. So, Y, so this is A1, A2, B1, B2, C1, C2, and at the secondary side this is A1, A2, B1, B2, C2, and this is grounded, and this is phase A, phase B, phase C. So, the connection is as usual. So, it is IA, and this transformer is 1:1, and this is I capital A, so this is I capital B. And here it is IA, this is IB, so here also it is IB, this is IC, so here also it is IC. Now, because this point N is not grounded, so I do not know its potential, so I say that this point is N, and as usual we take two loop current I1, I2 as we have done for YD transformer, and say this is I1. So, this is the transformer. So, this is the loop current. So, and this is my phase B, this is my phase A, and say this is my phase C. So, now here, so then therefore, if I do write down the loop equation for this, So, what I get is that V A, that is this rise, plus Z I 1, Z is the transformer impedance, then the reflected voltage from here. So, it is V A, then plus in this loop Z into I 1 minus I 2, then V C. So, Z into I 1 minus I 2 minus V C is equal to 0, right. So, V A plus Z into I 1 plus Z into I 1 minus plus this, and also plus and also another thing is missing here. So, this, then this drop, then this drop due to this, then in this zone I am coming Z into I 1 minus I 2, and then here this is minus V C, and then minus V small c plus V capital C is equal to 0, right. So, essentially we can write down, similarly we can write down the another loop equation for similarly another loop equation for I 2 can be written right. So, in the case of YD1, what we did, we have taken the voltage from here at here as the reflected voltage, but because here it was basically a transformer connection of 1 is to root 3. So, then therefore, this voltage was essentially coming out to be V, basically I mean this voltage divided by root 3 at this site. But here because this transformer connection is 1 is to 1. So, then therefore, this voltage would actually appear as it is. Please note we are doing all calculations in terms of per unit. So, then therefore, similarly another loop equation for I 2 can be written. So, from there this equation would be V C minus V A. So, this is wrong. Let us write down these equations again. So, from this I can write down that V A minus V N is equal to Z I 1 plus V A, and V N minus V C is equal to Z into I 1 minus I 2 plus V C. So, if I add them, what I get is V A minus V C is equal to Z I 1. This would be minus, this would be minus because I am going in this direction. So, this is minus Z I 1 plus V A plus Z into I 1 minus I 2 minus V C. That means 2 Z I 1 minus Z I 2 plus V A minus V C. So, this is equation 1, right. Similarly, another loop equation for I2 can be written. For example, if I write for in the loop CB, so essentially Vc minus Vn is equal to Z into I2 minus I1 plus Vc, V small c, and Vn minus Vb is equal to Z into I2 minus Vb. So, therefore, Vc minus Vb is equal to Z I2 minus I1 plus Z I2 plus Vc minus Vb to Z I2 minus Z I1 plus Vc minus Vb. So, this is equation 2. So, then therefore, after that we follow the same process, that solve for I1 and I2 from equation 1 and 2, right, and those solutions would be in terms of y, that is essentially 1 by z, and Va, Vb, V capital C, small a, small b, small c. And then we know that I A is equal to I1, then I say that I A is equal to I1 and I B is equal to minus I2 and I C is equal to, I C would be is equal to, it is entering, so I2 minus I1, I2 minus I1. And of course, we know that because it is 1:1, IA is equal to IA, IB is equal to IB, and I small c is equal to I capital C, right. I small c is equal to I capital C. So, from these 6 equations we get the expressions of I capital A, I capital B, I capital C, I small a, I small b, I small c, and then we write down the model IA, IB, I capital C minus IA minus IB minus IC is equal to Y sum matrix, 6 cross 6 matrix it would be, and then it is in terms of VA, VB. So, after that we do the partition and we get Y1, Y2, Y3 and Y4, right. So, essentially this is the same process as in the case of an YD, only difference is that instead of the line to line voltage for an YD transformer, essentially the phase voltage would be here reflected. and the other process is identically the same, other process is just identically the same. So, essentially this is the process, other than that there is no change. And of course, if our transformer connection is, let us say YGY and some x, then what we will do is that we will simply take the loop current at the secondary side, and then we will simply write down the loop equations at the secondary side by reflecting the voltage of the primary side to the secondary side, and then we will simply solve the loop currents at the secondary side. From there we will find out the line currents at the secondary side, line currents as well as the phase currents, they are the same because these windings are connected in star. So, after solving the loop currents by using the similar relations, we will calculate the line currents at the secondary side first. After we calculate the line currents at the secondary side, after that we will calculate the currents at the primary side. So, once we calculate the currents at the primary side and as well as in the secondary side, after that we will form the matrix. So, the process is absolutely the same, correct. So, I mean this is how we will do. So, of course, I have not essentially solved it because these are all trivial process. We have still many topics, many things to discuss. So, we are actually stopping this here as far as this modeling of YYg as well as YGY transformer is concerned, because we have already discussed the background for this calculation earlier. So, now we will now embark on the modeling of the only a DD transformer, which is only the last type of transformer which we need to discuss. So, let us discuss DD0 transformer. So, of course, by the same process we can also do DDX, where again x is 2, 4, 6, 8, 10. So, as we do that, well, first always our starting point is to A1, A2, B1, B2, C1, C2. Now it is DD. So, what we do is that we first make the connection at the primary side, and we say that this is phase B, we say that this is phase C, and we say that this is phase A, phase B, phase C. So, now if I mean let us draw the phasor diagram. So, in the phasor diagram this is A, B, C. So, this is phase A, this is B, this is C, and now from this connection I can say that B is interconnection of A2 and B1. So, this must be A1, A2, then B1, B2, and then C1, C2. So, you see, so as you can see that A2 and B1, interconnection of A2 B1 is denoted as phase B, which is indeed the case, phase B. interconnection of B2 and C1, that is denoted as phase C, and interconnection of A1 and C2, that is denoted as phase A. So we say that this is phase B, we say that this is phase A, and this is phase C. So C, B, A. Now because it is Dd0, so then therefore at the secondary side also phase A voltage of secondary side would be in phase. So again so this is again, so as usual, so it would be A1, A2, B1, B2, small c1, small c2, and we call this phase A, we call this phase B, and we call this phase C, right. After that we do the connection. So A2 B1 phase B, B2 C1 phase C, and phase A. So and then we denote the currents. So this current is in this direction IAB, this current is IBC, oh God, and this current is I capital ACA. Here this is IBA, here this is ICB, here it is IAC, and this is IA, IB, IC, so our connections as well as the phasor diagram are complete. Now from this connection what can I write about IA? Now from this I can write down that IA is equal to IA plus ICA is equal to IAB. So therefore IA is equal to IAB minus ICA. What is IAB? IAB is, so then therefore IA would be, IAB is Y into V AB minus VAB, and then minus Y, ICA would be VCA minus VCA, right. So therefore IA is equal to Y into VA minus VB minus VA plus VB minus VC plus VA plus Vc Va plus Vb minus Vc plus Va minus Vc plus minus Va. So Y is equal to 2Va minus V capital B minus V small c minus 2Va plus Vb plus Vc. So this is Ia, right? So this is Ia, and also from here I know that, also from here I would know that I should note it down, that Iba is equal to Iab, Icb is equal to Ibc, and Iac is equal to Ica. So we will use these relations when we would be going for calculating the secondary side currents. So we will continue with this, and we will continue with this derivation in the next lecture. Thank you.